So our next speaker is Jatin Batra, and he will be presenting on extreme simplicity bias of deep learning.
So this is a typical machine learning talk. So lots of pictures and no math. Okay, so this is joint work with. So this joint work with Jatin Mulwani, who was earlier at Google, now he's at Harvard, Praneet Tejapalli, and Prateek Jain from Google. So let's talk a little bit about the recent successes and failures of deep learning. So, for the past more than 10 years, deep learning has kind of changed the world of computer science in general. And here you can see lots of successes. So on the first row, you can see successes for image classification, and then you can see for speech recognition, and finally for machine translation. But despite these amazing successes, there have also been some very embarrassing failures. And here you can see a bunch of examples. So in the first picture, we see this example of a distribution shift. So what is that about? So suppose we train the machine learning model on the first row of pictures, and we want to test it on the second row of pictures. So while the objects might seem the same, but something has changed in the distribution, so to speak. And it turns out that here, deep learning fails miserably. And the second picture on the bottom is something which you might have seen somewhere else. It's a really famous example. People are able to really fool deep learning systems by making what are called adversarial attacks. So you can see here a stop sign on the left, which is recognized correctly with 99% confidence. But then you can see the stop sign with this a small ball-like shape on top of it. It's a green ball. And somehow with this little bit of editing, this changes to 80% sports ball. And again, imagine that, for driving, this is just really, really bad. And the last picture on the second row is another very infamous example. Nowadays, machine learning is being used and deployed in all kinds of real-world applications. In fact, in particular, even in law. So courts use it to decide how likely a person is to go back to crime, or this word recidivism, after being released. And to predict that, they use machine learning. And as you can see, say that this white man is low risk, and this black woman is high risk. So yeah. Okay. So so indeed, there are all these troubles, and it turns out that we can try to explain what happens in all of these three examples using a common framework. And that framework is simplicity bias, which I will now talk about in detail.
Will you also go to handle it?
A little bit, but that's not well understood, so not much. But yeah, I'll just say a few words. Okay, so the broad question is that why are neural networks brittle? So by brittle, I mean that they are very sensitive to these issues like, so here we had distribution shift, here we had adversarial attacks, and here we had bias amplification. It's really biased towards for race. So why do they have this brittleness? And how can we identify them? Is there a way to say, okay, this is the kind of brittleness this has? So to understand this further, here is a more concrete example. Let's say you want to train a model to distinguish between swans and bears. So how does a human being do it? So we say, okay, this swan seems to have this nice curvy shape, and it has these feathers which look like this, and and it has a beak and so on and so forth. And this bear has this this four legs shape and it's shady texture and this mouth and these ears. That's how we think. But is that also how a deep learning model trained would think?
But is that how we think, or we just take in the past, whenever we saw these people and so on?
No, I think it's not so much about the term. It's not about whether we call them a swan or call them a bear. So what is our mental model of a swan? Our mental model is these curvy features and the beak and feathers. But is it also the mental model which a machine learning system will create? So that's the interesting question, and let's look at that. Yes, so more precisely, there are like many features in a sense which are available. So there's a color of the image, there's the background, there is the shape, which I talked about in detail, and shape and organs. And you must look at all of these things when they construct a mental model of a swan or a bear. But does a neural network also look at these things? So let's investigate that. So this was the subject of two amazing papers by Gerhos et al., who looked at whether neural networks are sensitive to texture, and the second one is whether it's sensitive to bias or to background by Zhang et al. So let's look at the first paper by Gerhos. So in the first picture, you can see this image of a texture. Okay? And if people have seen elephants in life, this looks like an elephant skin if you know skins. And the second is obviously a cat. In the third one, but now if you impose this texture on the cat, then you can see this bold that your model will classify it as an elephant, whereas no human being would do that, I believe. So again, to point out the previous slide, you must look at a lot of things. They in particular look a lot at the shape, the organs, the face, the ears, and all. But the ML model is somehow not looking at everything.
I'll ask you, when do human beings make mistakes? What are the mistakes human beings make? They understand that.
It's a great question. Actually, this is an open problem. I mean, I think people talk about this, but it's not very.
Could you even say that it's something machine will actually better than?
Yeah. That's a good question, actually.
What is the question? What can mistake human beings make? What kind of? And then maybe it can be the machine better than. This old example, like. Very dirty in the night, it's get over. Then you most probably need this. That's opposite. So,
okay.
Answer recognition should work. And so, see the tumor. Doctors cannot say just see the tumor that it's benign or benign.
True, but this can be better off. Look at the second example. So here you have the problem of classifying water birds versus land birds. So on the first picture, you see this water bird who lives in water, and second the land bird who lives in the land. And you hope that the model will learn to look at the birds, but somehow, if you look at the second row, so this tool called GradCam, which tries to figure out what the model is focusing on using a heat map. So you can see in the first picture that the hot places are in the background, and so it's in the second image. And this is again problematic because if you look at the third image where you impose a land bird on water background, it ends up misclassifying as a water bird because it really just focuses on the background as a heat map. So the title of the slide says neural networks end up learning only some features.
Is there a concern that no matter how much data you give, this will have this problem?
That's a great question, actually. So I think it's not so much about like how much data, but it's about how diverse data and what kind of data. For example, one problem which I think at least I want to look at in future is whether something like this also happens if you work with let's say large language models, because that has been trained on a much more diverse kind of data than maybe these models, and how much of this bias still remains, and can you figure that out.
Good to understand the function of size of data, diversity of data, what kind of errors are there early on, how they change as on the axis.
Yeah.
That's a very
I think if you're looking at the same distribution, if you have like one particular distribution in mind, then I don't think more data helps. At least there's also whatever theory results later show, it doesn't really matter much. But what might help is if you have, if you add new kinds of data to help the network somehow.
Very difficult to
But I guess we are in early stages, so I would not be surprised if we. So there's a question we left with that why do they learn only some features, and can you figure out these features? Okay, so this idea of simplicity bias, simplicity here refers to the fact that they end up learning the simplest features which are useful. This was introduced by Shah et al. In 2020. So I will describe this using this example, which is in their paper. So here you can see this data set which has the red class and the blue class. And these two classes can be separated using two kinds of classifiers. So there is the green classifier, this is the vertical line. The green classifier has has almost no margin. What do we mean by the margin? The margin of a classifier here is the distance to the nearest data point. So for the green classifier, this is almost 0. It can also be classified using this a slightly more complex classifier, which is this zigzag wavy line, orange, you see. The orange classifier has more margin, so its distance from the nearest point is like far bigger actually. So I think the first line, orange classifier has more margin compared to the green classifier. And why is this an interesting thing? So margin is typically a good indicator of robustness. So in future you get more data which is closer to the line, then the orange classifier would still classify it correctly because it is far away from the points. Whereas if you perturb the perturbation, the green classifier will go wrong. Because it was so close, so if it's just a little bit on the other side, it will classify correctly. The authors of this paper used margin as a proxy for how good or how robust or non-brittle the model is. And they show that for one hidden layer neural networks, indeed for some stylized version of this data set, the neural network will actually end up learning the orange classifier. Sorry, end up learning the green classifier. So I think this is summarized on the next slide.
So what do you mean by it has the capacity? I think I could understand that it learns the green classifier.
Okay. So when we say capacity, it means that it is possible to represent the orange classifier using a different set of weights. But that set of weights will not end up getting that. Okay, so this is some algebra which not so important. So the important thing is the last line here. So here, we're looking at a ReLU neural network with k hidden units. So one hidden layer and the k hidden units. And if you look at the last two lines, so the linear feature, in a sense, ends up getting a weight of 1 over root k, whereas the non-linear feature, which corresponds to the orange classifier, that ends up having a weight of 1 over square root d. Okay. So that's a huge difference. And so with d is large, then this can be as extremely bad as you want. So indeed, the classifier is very, very close to being this green line. Okay. Okay, so to summarize, if you end up having this kind of behavior, simplicity bias, which is dependence on only a small number of features, then this causes brittleness towards distribution shifts and adversarial examples.
So how are you defining simplicity in the rates?
Okay, that's the contribution of our work that I'll go to later. Yeah, so this paper did not define simplicity bias. Just give an example. So we'll talk about it. So, okay, so but to summarize, simplicity bias causes the problems which we have seen before, because brittleness towards distribution shift and adversarial example. And in particular, if you look at this margin issue, then, like I said, if you perturb the point adversarially, or maybe if there's a distribution shift, then your model will not perform so well anymore. And this tries to explain the bad examples I gave in the beginning. Okay, so before I go on to define simplicity bias more precisely, I want to give examples of real data sets. So the previous thing was a made-up example, but let's also look at an actual example with real images. So so question is that how do you test if your real model suffers from this kind of bias? So you design an experiment. How do you design it? So so the authors of this paper, they combined two kinds of images. They took the MNIST dataset, which is for identifying single digits, and the second is the CIFAR 10, which is images, like images of all kinds of stuff, animals, and they combine this into one image. And if you put a 0, then it's a class 0 image. If you put a 1, it's a class 1 image. And and I want to classify class 0 versus class 1. And here is now the trick. So you train a model, of course, to classify, and then you randomize the CIFAR part. And it turns out that the logit, so what is the logit? The logit is a raw output of the model. So raw output of the model does not change. And that means that the prediction was not using the CIFAR part at all. It was using only the single digits. So this kind of it tells you more starkly that okay, even in real images, things like this happen. Focuses only on some features. Okay, and okay, here are some more studies of this. Won't go into that. And and this is also tested with all kinds of stuff, like all kinds of learning algorithms and activation functions. So it's not like only about ReLU or only data understanding.
Multiple layers.
No, multiple layers are also tried. That also doesn't make any difference. Yeah. Also tried with multiple layers.
So all the categories are labeled 0 and 1.
Yeah, of course. Okay, so okay, how do you fix simplicity bias? So I think the natural approach to fix it, which and also not a very good approach, is to use an ensemble. So instead of training just one model, maybe you train multiple models, and this is seen to help. So as you can see this picture, the this red line, which is encased in the this red highlight, and that shows that that's the new accuracy after ensembling, and the line at the bottom is
Why the text of the ensemble itself is multiple same?
Okay, so the idea is that if you train multiple times, then there is a better chance that. Okay, so when I say train, I don't mean train in parallel. I mean you train sequentially. So you train one model, and then you project out the features which it has learned. Then you train a second model, and then there's a better chance that second model will be able to pick up the stuff.
And project out.
Okay, so project out means that you just kill them from the input.
But how do you figure out what models are important for that? What is important for
yeah. Okay. So for that, you can look at the model itself. So you can look at the weight matrix and do something. Okay. So yeah, I'll talk about that in a bit more detail later.
But that requires knowing this. It's not
No, it's not any process. Yeah. That's why it's not the best thing to do.
Can you just explain this? What exactly you're doing between multiple models? Just immediately what are you doing?
Okay, so yeah, I think I explained this in a bit more detail when I define sensitivity bias. But yeah, I just leave it with the statement that ensembling helps, but it's not really the best approach. And like I said, it is limited to knowing that you're classifying, if you know what you're doing. And of course,
in the previous example where you combine the digits MNIST and CIFAR,
yeah.
Is there a sense in which it's going for a feature where the margin is smaller? You mentioned that it's going for a classifier which is a simpler description, but does it also have a smaller margin than something?
Yeah. That's a very good question. And so indeed, yes, because typically if you combine two features, you will end up getting more margin. And this is like a general statement. It's not just true about MNIST and CIFAR. It's always
so if you had looked at the picture, part would have gotten something the bigger margin.
Yeah. Okay, so yeah, I just leave it statement that ensembling helps, but this is also problematic in other ways. And in general, you don't want to make a system which has to train so many times. Yeah. And it really depends on knowing what a particular data is about. So it's not so good. The other thing which was tried is adversarial training, but this time turns out to not work well at all. So adversarial training is a very classic method to fix issues with robustness. So what you do is you perturb your image a little bit, and you generate new samples, and then you try to train. Turns out that it actually doesn't help so much. So the point that this is like wide open. It's unclear what to do. Okay, so now we talk about follow-up work. So here we so in a new work we define sensitivity bias formally. So here is an example. So you have this two-layer neural network, and let W be the weight matrix. And we say that the model suffers from simplicity bias if the rank of W is small. So, and why the same as learning a small number of features? It means that if you rotate your input, then in an appropriate basis, your model depends only on small number of features. And actually, this definition does not really require you to have even a neural network. This works even otherwise. So the point is that if upon rotation of the input, if there exists some rotation where model depends on a small number of inputs, then then you have sensitivity bias.
Just a single layer?
Yes, this is a single layer, but this works for any number of layers. Okay, so I mean, so this rank would work only for a single layer.
You do that each exposed to each neuron in the layer. And doubles are all the same.
Yeah.
That's very common. Right? Yeah, okay. It's specific, each double is specific weight. Big kind of things.
Yeah, exactly.
Layer, then you have like a.
Yeah, exactly.
Okay.
What is small?
Sorry.
So weighted by small layers.
Okay, so small here really means like a constant. So maybe a constant compared to your total dimension. So maybe your dimension is like 1,000, or your rank is like 20. So if it's like much smaller than the dimension, then something is small. And we'll see like two examples later. So you'll see what small means.
What empirically?
Sorry.
You written a definition of effective rank.
Okay, great. So so the issue with using just rank directly is that it is not robust to perturbation. So if you add like small entries here and there, that the rank will just grow up. So the more robust thing to do is to use some notion of stable rank or effective rank. So a stable rank is not a very good notion because it's like heavily biased towards one singular value. But effective rank says that you look at the entropy in a singular value. So entropy really captures how spread out the singular values are. So yeah, and that really captures what rank is. Rank is saying that, hey, are my singular values distributed across all my dimensions, or are they focused on the major dimensions? So entropy really captures exactly that.
What entropy is it?
Yeah, Shannon.
Is that the right example?
Well, okay.
There are other entropies which I thought were more natural.
Other entropy is like, which is more natural.
Smooth entropy. So you throw a little bit of the matrix, and then you can look at how many non-zero singular values are there, for example. Or this will be the smooth max entropy.
Okay, it's a good question. Yeah, no, we didn't do that. But
That might be more natural.
maybe.
Yeah, thank you. Something similar like if the first principal component, I think that is the emotional spectrum.
Yeah, I guess that's also what stable rank tries to do, in a sense. But yeah, I guess it's debatable how you pick.
We nominate the singular value.
Yeah, of course. It's after nomination. Yeah, because actually singular value is not so important, but what matters is how they are spread.
The Shannon entropy is affected by the profile of the power distribution. I mean, let us say there are some singular value at a certain level.
Right.
It's your. Then there's a step jump below. Then some more. You get pretty badly skewed. So if you, I mean, if you just want the rank, then I would say that throw the smallest few up to some external mask, and then look at how many.
Yeah, I see what you mean. Yeah. Yes, unclear. Yeah.
Yeah, go for it.
Okay, so with the aforementioned definition, here is our result. So we consider the following data set. So let's look at this in some detail. So we work with what is called the independent features model. So what is that? So here we first generate a label. So a label is either +1 or -1, and then condition on the label, we generate the input. So this is a bit going the other way around, but this is how the model is defined. So now your input has D features. The X0 feature is what we call a linear feature. So X0 is gamma times Y, so it is linear in the label. And the other features, the D-1, of those are called slab features. So it's called multi-slab. So what are the slab features? So if the label is +1, then your input is chosen to be +1 or -1 with equal probability. And if your label is -1, the input is 0. So as you can see, the other features by themselves, although they are sufficient for classification, they are not linearly separated. So only the first feature is linearly separated. And once again, your old idea holds that if you want a big margin classifier, then you want to be able to use all the features. Okay. And here is our main result. So yeah, so that gamma 0 will be some absolute constant which does not depend on D. Then if gamma is bigger than this absolute constant, then the max margin classifier on the logits will be such that the rank is 1. So what's the difference? So yeah, so when I said earlier that we are building a max margin classifier with large margin by using all the features, that classifier is not in the space of neural networks. That's some classifier which I can build separately. But if I were to look at the space of my one hidden layer neural networks, and then I were to optimize the margins, and then I would end up with a classifier with rank 1, and and in fact, this classifier would align only with the first feature. And why is this interesting? So this is because Jatin and Bach in 2020 showed that if you retrain your neural network, then as long as it is sufficiently wide and learning rate is sufficiently small, then you will end up hitting this max margin classifier.
So what do you say about is that not perfect?
Okay, so if your neural network is sufficiently wide and use gradient flow, which is like a really small learning rate, then from appropriate initialization, you will end up with this max margin classifier in the function space of the binary linear. Okay.
This is for something the kind of wireless that you have or more generally?
No, okay. So the result of Jatin and Bach is always true, but what we show is that if you specialize that result for this particular y index, then you will end up with a rank of W being equal to 1. So of course, if it was some other data set, then rank could be anything. But for this thing, the rank would be 1. Okay, and let me end with your question on real data sets and what the rank should be. So as you can see, the rank goes down to like really small, it's like around 10 or something. For Imagenet and also for this, so Imagenet is like a baby version of Imagenet. Yeah, we didn't have so much compute power to train at that point, so we train a small set. And Waterbird-Landbirds is a thing I showed earlier, to classify whether it's a waterbird or a blackbird. Yeah, that is like the question. So you want to come up with a regularization technique which can fix this. So assembling is one way, but it's not very good. And yeah, so if you could do this, that would be awesome. But we don't know how to make a regularizer like this. Okay, but yeah, this is a very good point and very good question. Okay, so yeah, thanks.
What is the proof for that experiment? I think more differential things you can actually argue.
No. So this definition of entropy is really only for the real data sets. So they're only for this. For here, for this thing.
No, even before. This one, this rigorous proof of simplified. So I imagine the way this will go is that we inductively argue that at least overtraining the rank is something and it's only going to a certain thing.
No. I think you're probably overestimating the result. So the result is really this, that you have rank exactly 1. This is like the real rank is exactly 1, not the effective rank. The true rank is 1.
Add the minimum. It's not really about what the dedication.
I don't know. Okay, so the result of Jatin and Bach says that if you train using gradient design, then you will end up with a max margin classifier in the function space, and that
is infinite.
Yeah, infinite, right? And that we prove will have rank 1.
Oh, so that is will have rank. But then, the entropy thing is for only for that.
So the entropy thing is only for this picture.
And there's somehow stable rank.
That doesn't work so well actually. So this stable rank doesn't work so well. So we try whatever rank gives a good picture.
And that it is not small.
Stable rank maybe not. So that's sum of all eigenvalues divided by the maximum.
Is it clear that large rank W will not have equivalence?
Large rank W. I guess I guess that depends on how you define simplicity bias. It's a circular problem. We define it like this.
I think interesting. Use something like a smooth max notation.
Yeah, that could be. Yeah, that I would imagine is a good idea. Yeah, I think it's something you should figuring out. So because research reviews of the paper and they're also complaining about that. Okay, the way we test is a bit better.
There are only three endpoints. So there is a smooth mid endpoint, smooth max endpoint, and very crucial is the channel combination. Often the real essence of the problem is captured in the other.
I see.
How big is the dataset?
So
Can you do it there?
that's a great question. So this used like I think several days of an 800 GPU. Of an 800 GPU.
800 on 1 GPU.
I mean, if we were to use one GPU, then it would take several. Oh, okay. So the overall time to run all the experiments is like a month or two on a GPU.
But just one GPU
No. I mean, if you had one GPU multiplied, so yeah. GPU hours is like a month or so. So I don't know if you could do it in TIFR. I mean, the GPU may not be that great, right? It's 800 GPU. That's like double line.
So that's these two bands and three bands and two bands.
Yeah, that's
this one. So if you do experiments and find that it gets exactly outputs exactly something the same.
it comes like really close to being straight, actually. Like, yeah, in fact, extremely close. So of course you want that exact, but even experimentally. So even if you use like more than one layer, even then.
So then the question is there something else that is being maximized or minimized, right? Because it's not exactly state. There is something about the margin that is also playing a role. Maybe it's in a very mild form, but if it is not exactly state, there is something else also at play.
No, but I think the not being exactly straight is just because of the randomness. So they always be a little bit. Yeah, I mean, if you initialize differently, you will end up somewhere else. That's always the case. So like even when I like say these things, these are with high probability, some probability.